Thanks for the intro. So before I begin, I'd like to thank Alan Brent, who's my supervisor, for recommending I come here to present my research, preliminary research, and Brad Mugdway, who is also doing this research with me. So 1 second. Here we go. So welcome towards a more effective hybrid energy system for residential households. This presentation is about the research I'm planning to conduct over the next few months for my master's dissertation. Let's dive straight into it. Electricity New Zealand. So 34% of electricity consumed last year was by the residential sector. Low temperature heat makes up to 50% of the residential demand. And this ratio is very consistent across the years. As you can see, it's always hovering around 50%. Now keep that 50% in mind. We're going to look at the whole picture here. So out of that 50%, half of that ends up being space heating, and the other half basically ends up being water heating, which means that out of the total electrical demand of residential households, 25% of the end-use energy ends up being space heating, and 25% ends up being water heating. To further elaborate on my point, this is taken from the Green Grid study, and this depicts the top 20 peak half hours that was recorded within their data of the 50 houses that they studied. And as you can see, hot water and the heat pump are very significant here, on some days making up to almost 60% of the peak load during these morning and evening peaks. And the morning peak here is present for higher frequency than the evening peaks. So Anya mentioned yesterday that the best way to heat is with heat. And that brings me to my basic design. So this is the hybrid energy storage system. It's got a few components. Some sort of solar collector. It's going to have two types of storages, a temporary storage and a thermal storage, a long-term thermal storage. So at the moment, I'm eyeing PVT for my solar collectors. And so how the system will work is by PVT heating a medium, which will be directly stored in the long-term storage. The electrical output from the PVT will go to a temporary storage, and both storages will be controlled by a control unit, which will have a dynamic response according to the demand profile. Heat will be directly used in some applications straight from the long-term thermal storage straight to the house. I know it's not shown there on the image, but it's something I'm working on. And the extracted heat flow arrow that's shown there, depending on a couple of the designs I've been working on, I should be able to extract heat out of the house. So space cooling and space heating are both going to be effective in this system. The whole system will have various sensors. The whole system will have sensors placed in various places, allowing an elaborate control algorithm to be implemented. Budget expectations. So I'm expecting to achieve cogeneration, 20% electricity, 50% heat. That's just pretty standard of PVT panels these days. And the direct use of heat for certain applications like hot water or spatial heating will allow me to meet the demand with primary energy, which means we can ignore all the conversions that are typically done, like from electricity to heat and such. And we're seeing heat is very substantial. So serving heat with heat should lower the dwelling's overall energy consumption, I theorize. The system will be localized, and it will have off-grid generation. It will have low to no emissions, depending on, well, transmission-wise at least. And the system will be reliable and highly dispatchable. Objectives of this research. So I'm planning to integrate these existing technologies just using off-the-shelf components, so it's readily available and should be quite easily integratable into existing households. So I'm looking to create a dynamic energy storage system. And in order to do that, I need to develop a functioning control theory, which will allow the entire system to operate optimally. To do that, I am thinking about implementing some sort of fuzzy logic, as it allows more dynamic responses. And of course, making sure that the technology is functional along with sustainable, affordable, and reliable to help meet the energy trilemma. For my literature review, I looked at solar generators. Everyone's heard of PV, generating electricity from light. There's solar thermal, which just generates heat. And there's PVT, which or photovoltaic-thermal, which is a combination of the previous technologies. It generates electricity as well as heat. So one of the benefits about PVT is that you get a lot more value. Because they're a lot more efficient, you get a lot more value from the same land use within the same fingerprint. PVT is substantially more efficient than PV panels. And The other hidden benefit is that PV panels typically, when they like most of them are about 22% efficient or so, and as they absorb the radiation, the irradiance throughout the day, they only convert 22% of that to electricity, while the rest of that is just dispersed as heat, which also in turn lowers the efficiency of PV panels. With the PVT system, we're taking heat away from the panels, which means the panels will continue to work at an optimal level. I've looked at energy storage systems, energy storage as well. So looked at batteries. So batteries are good chemical storage. They're getting cheaper these days, and there are recyclability concerns. But EVs are also on the rise. So for one of my use cases, I'm thinking about implementing a vehicle as the temporary storage. I also looked at flywheels, which are good mechanical storages, short term, and they do have a bit of a higher upfront cost. But there are a few residential cases being done these days. A startup called Taurus has a residential flywheel available these days. Also looked at geothermal systems, open loop and closed loop, and what attracted me to geothermals for my long-term storage is the high coefficient of performance. So if I use a geothermal heat pump, I can get a high coefficient of performance around 300% at least. And basically what that means is energy into the system tends to be higher than energy out of the system. For my research methods, I was thinking about, so all this is going to be simulated on Simulink, and for the locations that I'm thinking about simulating it are Auckland, Wellington, and Christchurch. However, I have been debating swapping Wellington for Dunedin, as Hannah's presentation yesterday revealed that houses in Dunedin use more heat for just space heating and stuff, obviously because it's colder down there. So I might swap that out. But most of my demand side data, which I will be simulating, will be based upon the Green Grid study, which studied about 50 houses across a year back in 2014 to 15. And majority of those houses were in the North Islands, mainly New Plymouth, I believe. So a bit of normalization or averaging will have to be done to make sure it's viable for the South Islands. I'm also looking at Heap 1, which has some useful data, but that's even older. So kind of waiting on Heap 2, but we'll see what ends up happening. For my control system, I've talked about fuzzy logic, and in the end, I'm expecting to compare the efficiency of my system design with other regular PV and evacuated tube systems, and obviously comparing the cost as well to see if I can justify whether this system that I'm developing is going to be worth the extra cost, the high upfront cost. For conclusions, this is all just ongoing work at the moment, so I don't really have any conclusions. So I thought I'd just talk about my assumptions and limitations. So high resolution energy data is quite easy to find, but high resolution power data is tough to find. And the Green Grid study had the best confidence interval I could find because it's got power draw data at 1 minute intervals. So it's got a very high confidence interval. However, a lot of that data, as I mentioned earlier, will have to be normalized or averaged, as it doesn't quite represent the South Island as well. For my challenges, thermal analysis and electrical analysis are quite critical to understand what's going on within the system, and it will also help me develop my control theory. Integrating these technologies and observing how it functions under very seasonal conditions is also going to be quite intriguing. That's basically it. Thanks for listening.
Great, thank you. Do we have questions for Rishi?
Thank you very much. In your initial scoping, what was your rationale for not having something from the South Island? Sorry, from the south of the South Island. And I don't know, it's appreciate your, volunteering that you might include Dunedin, and that'd be wonderful for us. But you must have had some initial reasoning at the start.
Yeah, so my initial reasoning was I was just going to go off population density, and Auckland, Wellington, and Christchurch are the biggest cities in New Zealand. So I thought just applying it to like the majority of the population would be good enough. But obviously, like after looking at a lot of these presentations over the past 2 days, I have been thinking Dunedin would be a better fit within the study.
Yeah, so the question is, can Dunedin represent the canary in the coal mine kind of situation, or represent the experience of the south more generally?
Sorry, I don't quite understand that question.
I think it's just adding to that argument, sort of, represents an extreme.
So I just have a question about your long-term storage. So are you thinking about seasonal storage for that long-term storage, and is that geothermal, as in using the ground basically to store the heat?
Yeah, so from some geothermal data that I've seen, if you dig about maybe 5 meters or so, even temperatures beneath that are quite stable in the ground. So for my long-term thermal storage, it's either whatever type of storage it ends up being, it will be probably underground to keep the heat compact and within the system, allowing minimal losses. And I'll probably use like a ground source heat pump or something to help push that out, to push the heat out.